Hey, good morning, everyone, and welcome to the informal seminar for this week. We're very happy to have Bart Ripperda telling us some stuff about black holes. So Bart received his PhD from Leuven University in Belgium, and then spent some time at Goethe before becoming a joint postdoc between the Flatiron and the university. Next year, he'll be joining faculty at SIA, but we're lucky to have him here for a year with us as a member. Bart is an expert in many things, but especially high energy astrophysics, especially in the context of environments of black holes and neutron stars. He's worked on extending current methods and kind of thinking about the physics, connecting kinetic effects, plasmas to observables, non-thermal stuff, also how do you do simulations and so on. And so today he's going to tell us about or help us address the question of how do black holes shine.
Thank you very much. Yeah, I have to say this, I changed my title slide recently. Hi, Kako Beyond made this, and I liked it so much that I thought I should show it. So it's the EHT image of the polarized light together with the current sheet from simulation. So it's an artist impression, it's not. It's cool. Right. So like, I got this question many times, like, why do we even care about black holes? Why do we do the research we do? Well, here at the IIS, and also at the university, it's very clear to say to study quantum gravity, which most people in this room do not, like deviations from GR actually. But as astrophysicists, we're typically more interested in constraining cosmological models and understanding the role of black holes in the centers of galaxies, at least supermassive black holes. How they form, how they relate, how they feed back, how they got to their size. So if you look at the Hubble deep space image, then you see all these galaxies. Actually, I think there's one star. If you can point it out, by your lunch. We have no information here that there are. You found it?
Well, it's diffraction specs.
All right. Yeah. So yeah, we don't know, from this image, we simply don't know that there are black holes in these galaxies because we don't see them with visible light. But at some point we started looking at radio waves, and we started seeing jets from some active galactic nuclei. And particularly interesting was that these outflows are like very energetic, highly relativistic. So they had to be powered by something weird. It practically couldn't be a star. And also the light coming from the center here indicates that there is something highly energetic there that is most likely a supermassive black hole. So I'm not going to talk about any of that. I want to talk about a different phenomenon that we see also from supermassive black holes, and that's flares. So there are important questions in our field of understanding this environment of black holes. What powers these jets? What drives accretion? And how do supermassive black holes emit such a broad radiation spectrum up to very extreme energies of TeV or even higher? But there is additional info. We have these rapid flashes of light, very bright light, that come from either nearby the event horizon or from the jet, that are transiently as bright as the emission coming from the disk or the jet itself. And here is an image of Centaurus A by Michael Janssen and EHT. There are no flares here. I'm just trying to point out where people typically think that the flares may come from. So either from the jet or from at larger distance or from the horizon. So typically those flares have been observed for, let's say, 20 years. And typically there is an analogy with solar flares in the sense that there is a large reservoir of magnetic energy that can be transformed to heat and kinetic energy. But around black holes, we don't know how that exactly happens, because in the sun we observe these kind of loops that erupt, and in that way release their energy, as you can see in the video on the right. On black holes, such loops cannot exist by the Noether theorem. So there has to be some other mechanism that releases energy if this analogy holds. So the question is, where do these flares form and what mechanism powers them? And if we understand that, what can they teach us about the nature of supermassive black holes? So if those flares are powered from the horizon, then that means that we need to understand extreme plasma physics at the event horizon. And with extreme, well, I'll tell you what that is. We're lucky to be in an era that we have a lot of multi-wavelength information coming at us, and there will be more in the upcoming years. We have bright TV and X-ray flares from ME7 with potential radio counterparts. As you can see here, we have the radio polarization image of ME7 and the radio image of Sagittarius A star. We have infrared flares from Sagittarius, and here you see an example of the gravity observation, which even managed to link such a flare to an orbit. And we have X-ray flares from Sagittarius star, potential radio counterparts. And recently I learned that there are also X-ray flares from M31 from Andromeda that actually look very similar to the X-ray flares from Sagittarius A star. So this is very, very interesting.
Why just supermassive and not stellar mass black holes?
You have to make a choice where you spend your time on. No, I think stellar mass black holes are at least equally interesting. The reason I talk about, I'm not even just talking about supermassive, I'm talking about low luminosity AGN in this case, because they're the simplest in a sense. We know fairly well what the properties of the accreting plasma are, depending on who you ask, but we know it at least better than disks that are cooled and thin. There are even like basic principles of the accretion are not fully understood. They flare too. We see very interesting X-ray flares from Seyfert galaxies or from X-ray binaries. The mechanisms may be very different. There, you actually may expect loops that connect between the horizon and the disk that look a lot more like those solar flares. Something that I'm very interested in as well, but it's much more complicated because of the interplay between radiation QED effects and the plasma. 10 more years, and I'll give that talk. So the regime of relativistic plasmas that we need to understand for the environment of a black hole, this extreme environment. One of the typical quantifiers of how relativistic a plasma is the magnetization, sigma. So it's the magnetic enthalpy density over the rest mass enthalpy density. I have a density here, it should actually be an H. It's a sigma cold anyway. So sigma is very small on terrestrial plasmas. For terrestrial plasmas, like in the tokamak or in the Earth's magnetosphere, it can still be magnetized in the sense that gas pressure is much smaller than magnetic pressure. It's not relativistic. In black hole magnetospheres and neutron star magnetospheres, sigma is typically can be much larger than 1. In accretion disks, it's not necessarily the case. But if we look at these types of systems, particularly for low luminosity AGN, then the mean free path of electrons is larger than the system size. So the plasma is collisionless. It's magnetized, meaning that the alphane speed is close to the speed of light, which is an assumption often used. And that also means that we have to deal with Lorentz factors that can be much larger than 1. There's a huge scale separation here. Typical particle motion, let's say the Larmor radius of the particle is much smaller than the system size. And all of this together gives you a large reservoir of magnetic energy. And together with the collisionless nature, it's an ideal system to accelerate particles and power high energy radiation in the form of flares, for example. But there is a step in between, like magnetized plasma itself, it doesn't radiate. Like you first need to dissipate that magnetic energy. So if the plasma is purely highly magnetized, it will not do much. So the question is, how does it demagnetize and how does it dissipate? It's a very difficult question to answer because in principle, to do this fully from first principles, you need special relativity. You're dealing with highly energetic and magnetized plasma. You need general relativity, obviously. You need kinetic theory because the plasma is collisionless. You need the radiation and quantum electrodynamics effects that have an effect on this radiation. And all of this you typically need to do numerically. There's not too much you can do analytically. So you need numerical methods that can deal with this huge scale separation. You need very high resolutions. What you would like to do is solve this set of equations This is the Vlasov equation coupled to the system of Maxwell's equations. It's in flat space-time here. I will not go into too much details. Mooney and Leff can talk about that another. They know much more about it than I do. I just want to say, in principle, you want to solve this system of equations because you know the plasma is collisionless. It's very hard to do so because this is a multidimensional, highly nonlinear many-body system. So you would need a particle and cell method, and yeah, it's hard to do that on global scale. But what can we learn from observations already? Like which mechanisms that fit in this kinetic theory can accelerate plasma? As we said before, there is an analogy to solar flares where people often invoke magnetic reconnection being responsible for the particle acceleration, the dissipation of the magnetic energy. Here you see an example of a, let me play that again, of a loop on the sun that reconnects. It's obviously an artist impression here. So what happens is that a large reservoir of magnetic field that can accelerate particles and by transforming the magnetic energy into kinetic and heat. But we've observed that actually, or claims that that's been observed. Here, a Nature paper from last year, where you actually see two field lines here pointed out by the purple and the yellow coming close together, and here they reconnect and they form a new, they change topology practically, they form this kind of X point in the blue. And there are claims that even plasmoids, like energetic blobs of plasma as a result of the reconnection, are seen as these bright features. Not responsible for this observation. So don't take it on me if you don't believe that these are plasmoids. This whole process is reasonably well understood from first principles kinetic simulations. And this is an example by Greg Werner. And what you see here, if we go back to Wikipedia level reconnection image, is that field lines, anti-parallel field lines in 2 dimensions here, they are they move together, they form an X point, and the upstream plasma here is highly magnetized. Sigma is much larger than 1. The inflow of the plasma into the X point goes with E cross B velocity, and you form an electric field that can accelerate particles. That is, for this collisionless case, is about 10% of the magnetic field. In MHD, it's smaller. I can tell you why. If you simulate this with particle and cell, then you see that the current sheet, the reconnection layer, it tears and it forms these plasmoids, these tiny blobs, and those blobs, they can grow by merging. They can bump into each other and merge to larger structures. And you end up with these kind of monster plasmoids, which are typically filled with non-thermal radiating plasma, in this case, PER plasma. What is interesting now is that the acceleration of particles due to reconnection goes with the sigma of the upstream plasma. So the more magnetized the plasma is, typically the larger Lorentz factor you can accelerate to, as you can see here in this plot by Cironi. There's some caveats to that. In 3D, for example, I will not go into that, but in principle, this is true. The more magnetized the plasma, the more you can accelerate. And that's, of course, interesting if you have such a huge reservoir of magnetic energy around the black hole. So what do we know from observations? From ME7, I already showed this plot in the left bottom corner. We saw bright TeV flares in consequent years. And most interesting are the ones in 2008 and 2010, because there we see an X-ray flux measured with Chandra coming from the core. So we can really say, like, okay, these TeV emission, if linked to the X-rays, then it may come from nearby the black hole. The variability time scale is of the order of a few days of this emission. If you look at the light curve and the emission region, by very simple causality arguments, it can be pointed down to the order of a Schwarzschild radius. It's a hand to AVR. Like, it's a small emission region typically. So reconnection could do that in principle. And the question is, does it happen somewhere close to the black hole? I already mentioned it's very hard to simulate that with these collisionless methods because the scale separation is so huge and you cannot resolve the plasma scales that are necessary together with the global scales of, for example, the jet, which is of the order of 1,000 light years, whereas the typical orbit of particles in reality is 10 to the minus 11 Schwarzschild radii, so the typical size of this dark region. It's impossible to do at realistic scales. It's even impossible to do in 3D at unrealistic scales at the moment. So there are no global kinetic simulations of black hole accretion disks in 3D. There's one paper I will discuss a little bit later that made the first effort. The issue here is, of course, that we know that those global and plasma scales, they do interact non-linearly through instabilities, reconnection, dynamo, turbulence. So we cannot ignore the small scales to understand the large scales. Well, luckily, we have magnetohydrodynamics. It's scale-free in its ideal form, and it captures at least some of the global dynamics. I think a lot of the global dynamics, but we can debate about that. At least the accretion and the jet launching to first order. That can nicely describe those systems. So MHD, fluid approximation, you probably all know this. You can reduce your Vlasov equation by taking moments to a set of variables, the mass density, the velocity, the energy, and the magnetic field. And it looks something like this in covariant form. You have conservation laws and you have still Maxwell's equations. What's typically done is an ideal MHD approximation. The plasma is collisionless and it's single temperature Maxwellian. Both those assumptions are wrong in the jet and in the accretion. To what extent they're wrong is a good question to ask, but in principle, they're not correct. And additionally, the plasma in the ideal MHD is considered to be a perfect conductor. So you have a vanishing electric field in the local frame, in the fluid frame, which means that not only that there is no reconnection in theory possible, numerical codes is of course possible, but in theory it's not. And there is no accelerating electric field. So you cannot probe particle acceleration in ideal MHD. There is one small step that you can go beyond ideal MHD, that's resistive MHD. You can incorporate some non-ideal effects, by no means collisionless effects, but you can introduce a resistivity that allows the magnetic field to change topology and to release energy. It can be ohmic heating. It's particularly hard in relativistic MHD because there is a stiff source term and you additionally have to solve Ampere's equations. It looks something like this. I will not go into too much detail, but in principle, it means that even if you have a numerical method that can do it, which is not too hard, it requires high spatial and temporal resolution, because if you put a resistivity, but you're not actually resolving the spatial scale, then you might as well not do it.
Sorry, why you say there's no accelerating electric field? You still have V cross B, right?
But V cross B in principle can only accelerate a particle if it's already non-Maxwellian. Like if a particle is in a Maxwellian distribution, then the V cross B, the electric field from V cross B cannot do work on the particle. So yeah, if it's Maxwellian, it will remain Maxwellian. So can you probe reconnection in this resistive MHD framework? Yes, you can. It looks fairly similar visually to the particle cell simulation by Greg Werner that I showed. You see plasmoids, you see field lines reconnecting. You can even slightly improve this. Sebastian Selvi is doing this in Amsterdam for his PhD. You can derive resistivity models from particle and cell simulations by inverting Ohm's law. And you can plug that resistivity into the MHD equation, and in that way you can get your reconnection even a bit closer to particle and cell. In particular, you can speed up the reconnection rate to this 10% that I mentioned before, 0.1 of the speed of light. That's also not necessarily the correct physical thing to do. It's more of an ad hoc approach to get closer to what particle and cell tells you. Advantages of MHD here is that you can use mesh refinement. You can really zoom into the dissipation layer and avoid resolving less dynamic regions. As you can see here, the resolution is really focused on this layer, while in the upstream, that's a typical feature that some MHD codes have, like Athena and the black hole accretion code that I used here. It majorly speeds up if you're looking at reconnection. If you're looking at turbulence, I mean, the whole box would be refined. So also there, it doesn't help you that much. Okay. Next question. What do we know about the magnetic field around black holes? Well, we have the typical Blanford's Nyack picture here. toroidal field, so in plane field here, is dragged into the black hole. It starts to co-rotate in the ergosphere if the black hole is rotating, and in that way, this initially a toroidal field line is dragged around. It creates an out of plane, a B phi, and in that way you get a pointing flux that can create a strong jet. GRMHD simulations have reproduced that. I'm showing Sasha Tchaikovskoy example, but I think there have been thousands of these simulations showing indeed that if you put a fluid here, a magnetized fluid, it will be dragged into the black hole and will form a strong jet or weak jet. So what else do we know from observations from the EHT? Well, actually not from the EHT. We know the jet power to an order of magnitude for MED7. From that jet power, if you believe that Bland-Wapsnayak mechanism to be true, then you can calculate that the magnetic field at the horizon needs to be of the order of 100 Gauss. It can be 10, it can be 1,000, depending on which jet power you take. But this 100 Gauss at the horizon roughly matches with what the EHT also found by matching the flux of the image. I think it's about 10 Gauss at 7 Rg, and if you think about the radial dependence of the field, then you get to an order of magnitude of 100 Gauss at the horizon. I'm by no means claiming that it's exactly right. We also know that the macroscopic size of the image, let's say of the Schwarzschild radius, is about 10 to the 8 kilometers. And the microscopic size of the Larmor radius of a particle in MED7 is about a kilometer. And the mean free path is much larger than 10 to the 8 Schwarzschild radii. So this is truly collisionless plasma, meaning non-thermal effects are important. Particles can accelerate before colliding. GRMHD treats the plasma as a collisional thermal fluid, which means the electron temperature is unknown, and we typically paint it on. We can do a pretty good job, but we don't really understand what the electrons do from first principles, which gives us a major uncertainty in interpreting the radiation from the image. Right.
You say a few words about where do these values put you in this parameter space of sigma that you introduced before?
What exactly do you want to know?
The numbers that you just gave for scales, where does this imply for the value of sigma that you introduced before for magnetization?
Oh, I mean, yeah, hard to say. Like sigma doesn't only depend on the Larmor radius scale, let's say.
I thought you introduced sigma as the ratio of the magnetic energy density to the resonant energy.
Yeah, but there's also pair production typically. So you can produce plasma in situ that can really change your density by quite a bit.
So you do not know whether sigma is ordered unity or much larger here?
In the accretion disk, based on MHD simulations, we know that sigma is order unity in the disk, and that is sigma of the total plasma ions, let's say, dominated by the ion mass. Sigma of the electrons, I think we don't necessarily know. In the jet, it's even harder because in the jet and MHD simulations don't give you a realistic sigma. You need to inject density for the simulation to remain stable. And even if you don't, then the sigma that you get from the simulation doesn't necessarily represent reality. You would need to know how much pairs are produced close to the horizon to understand what the sigma would be. You can estimate that based on observations. I think George can tell you probably more about that. He has a paper on this. It's still only known to an order of magnitude. Like sigma could be 10 to the 8 close to the horizon, could also be 10 to the 6.
Okay, that's good enough. Okay. And the second issue, you mentioned QED before your talk. We actually have to work out QED effects at this in this context. You want to understand, the basics of what is going on.
So this light is thought to be coming from the disk, I think, which means that QED effects there are not important. QED effects are important in the jet, which we with MHD simulations cannot probe, and with the EHT radiation, well, we think at least that we're seeing light coming from the disk. But Leah, George, correct me if I'm wrong, because I'm not an expert in it. So EHT tells us even more. We saw polarized images, and based on these sort of toy models, ray trace models, which I really like, you can put a toroidal field, radial field, and vertical field and see what an image would, polarized image would look like. If you compare these three with actually observed image, then it becomes immediately pretty clear that there has to be a strong ordered vertical field present, which will remind you, if you're familiar, to a magnetically arrested disk. And this was proposed by Igumenchev and Narayan. I think this drawing is actually very wrong because I think the field lines will never look like this, but like you get the idea that like there is a vertical component to the field here, and that can impede the accretion. It can act as a barrier. And again, Safra-Tchaikovsky simulated this, many others after him. And you see here, again, you see the jet, you see the disk, and you see this vertical barrier form. What we did, we simulated such a magnetically arrested disk in 2 dimensions. There are many caveats of why that wouldn't work as well, but I'll not go into that. But what we saw was if we did this with resistive MHD at very high resolution, capturing the resistivity that we put, then there's not only this vertical field here, but there is also a practically horizontal field at the horizon during what we call flux eruptions. I'll explain later what that exactly is. And this is a current sheet. The current sheet forms and reconnects nearby the horizon. So in 2D, there is some indication that there could be flaring mechanisms. What's now particularly interesting is that this current sheet is being fed indeed by the plasma in the jet, which, as you just asked, actually is highly magnetized. So there we have a reservoir of magnetic energy. Well, how do we do this? We used AMR, 6 levels, effective resolution of 12,000 by 6,000 to make sure that we capture the reconnection layers by more than 10 cells. And if you zoom in, I hope I convince you that indeed we're resolving those reconnection layers. You can see here that they're well captured and that you're even resolving mergers of these blobs in 2D. Right? So how does this work? This is a typical idea behind this magnetically arrested disk. You have infalling plasma with a pressure that is larger than the magnetic pressure. It drags in, say, turbulent magnetic field, not necessarily ordered is what I mean with that. And that field strengthens the jet. So a field line falls onto the black hole. In principle, the field line itself doesn't know that it crossed the horizon, but to us, once it crossed the horizon, it looks like there is an outgoing field line in the upper jet and an ingoing field line in the lower jet. And if you keep doing that, you stuff the jet with more and more magnetic field, so it gets stronger and stronger until the point that the jet becomes so strong that it can suppress this inflow here, funnel, into a very thin layer, where now the field lines are practically anti-parallel and equatorial. And this here looks exactly like a current sheet. You can simulate that. I'll show you this later in detail. But in principle, it looks like this Wikipedia picture. And what's now interesting is that if you look at the horizontal field here that represents the field of the jet, let's say, it creates a field with a vertical component that moves outwards. Like this loop will fall into the black hole, but this loop here can move away. And so you're creating vertical field, and it's stretched out further the more it moves outwards. And that vertical field is your barrier that can push away your accretion disk. And you also see this in simulations where you're piling up vertical field here practically in the outflow region of the recognition.
Can I ask a question?
Sure.
Could you remind me, in these simulations, the toroidal field that you get, is that actually, in the, let's say, the 2 hemispheres, so to speak, pointing in the same direction, so you would not get reconnection from the toroidal field?
No, in the 2 hemispheres, I'll show you. I'll show you in a second. Yeah, it does reconnect. The toroidal field does reconnect. Okay. So to answer this question, actually, we did a simulation in 3D, very high resolution simulation. I don't know if it's now still the largest. At the time, it was the largest. So forget about that claim. But what you see is that this is your typical accretion state. And at some point, you see that also here in 3D, thin layer forms and your disk is pushed away. Now this thin layer is not axisymmetric anymore, and it's still transient. But what's interesting is that the transient is different than in 2D, and this is a magnetic flux that builds up on the horizon. So you build up, you build up, you build up until you hit this magnetically arrested disk point where gas pressure becomes equal to magnetic pressure. And then you start to erupt, you start to eject flux, and your magnetic flux on the horizon goes down. This period here of the flux eruption is the same as in 2D. It's set by the reconnection rate, simply because that's all that's happening. Reconnection is ejecting this flux. So this rate is set by the reconnection rate.
So sorry, can I ask why the 2D reconnection rate you found is same as 3D?
They're both dominated by the tearing instability. And if you have reconnection at a Lundquist number that's higher than about 10 to the 4, then you get to an asymptotic rate of 0.01 times the Alfvén speed in MHD.
So I guess this didn't enter into the turbulent reconnection region.
I mean, the reconnection is very, very turbulent. I can show you.
No, because if it's in turbulent reconnection, this can go beyond 0.1 VA at the Alfvén speed. So I just wonder why there's a limit on the reconnection rates.
I think also in 3D, if you have high enough resolution, you will see that turbulent reconnection gives you a 0.01.
I'm just saying it's about 0.1 Alfvén speed.
0.01.
0.1. Yeah, we can discuss this later.
Sure,
Yeah.
sure, happy to. Well, let me just say that me and others did very high resolution simulations with the resolved resistivity and viscosity. And we measure reconnection rate, and at very high resolutions, we find a rate of 0.01 in our simulations. Maybe our simulations are wrong, maybe our methods are wrong, but we consistently find 0.01 times the Alfvén speed if we have high enough resolution. At low resolution, we find 0.1 Alfvén speed rate. But that to our interpretation is that then we are not resolving the scales to get to a high enough Lundquist number to get into this asymptotic regime. In any case, in this simulation, we find a 0.01 rate in 3D. And it's interesting. Where did I leave? Yeah, what's interesting is that now in 3D, the accretion phase lasts longer. And this is an artifact that was pointed out I think by Charles, for example. In 2D, this magnetically arrested disk cycle, it sort of goes into magnetic arrest like all the time, because you cannot build up accretion on different phi angles because you're not simulating them. So in 3D, suddenly magically the accretion period is much longer, and that accretion period roughly matches the time in between flares from Sagittarius A star, very roughly, or to an order of magnitude. In 2D, it definitely doesn't match. The flare cycles are way too fast. If we zoom in, actually, you can see that the reconnection here is also pretty turbulent, and you still see features that look like 2D plasmoids, but in reality now they have a 3D extent of sort of flux tubes that can kink, and yeah, much.
So the color here is showing which quantity?
Good question. Plasma beta, I think. So gas pressure over magnetic pressure. So the takeaway here is that in 3D, we get a transient and non-axisymmetric macroscopic reconnection layer at the horizon of about 10 Rg in this case, but we see different sizes. And the accretion disk is ejected over a part of the phi angle, or part of the out of plane angle here in these sort of duty cycles. All of this was well known before this simulation, except the reconnection part. And what's interesting is that what reconnects is the jet's magnetic energy, and you see here from plasma beta, it's pretty magnetized here. In reality, it would be even more magnetized than in MHD simulation. So there's a lot of magnetic energy available. And what's even more interesting, maybe to a plasma physicist, is that it seems that reconnection here is not only essential to power flare, but it's essential in this accretion duty cycle to redistribute the flux in these magnetically arrested disk cycles. How that exactly works, we don't know. How does that flux act when it's being pushed back into the disk? It's something to be found out. We have some ideas, but yeah.
Can I ask you a question?
Sure.
So you said this is plasma beta, right? What would like the density look like? Would it also be like this thin or would it be a bit broader than what we see here?
In the blue region, you mean, or
I mean, the density of
Or
the
here.
matter. Yeah.
Yeah,
Would it
here
be
it's
that
high.
thin?
it's that thin? Yeah.
Okay, so
Yeah.
it doesn't have like a kind of a slower.
No. So sigma and beta. So sigma practically representing what you got, like least squared over density.
Yeah.
It looks the same. Yes.
Yeah.
It's both pretty thin. You can ask a question if that's realistic. I'm pretty certain in the layer it's realistic, but it's set, how thin it is set here by the resolution. Like this happens on the scale of 1 cell, like it's ideal MHD, you couldn't do this in resistor. And the surrounding density is floored. So what would it do if you could do a pair production here? Pairs would probably be sucked into the reconnection layer. It may look different. It's very hard to do though. But yeah, it's definitely an interesting question to understand.
Have you done ray tracing of these kinds of things? I mean, 3-dimensional version?
Yeah,
Is there any difference in the image?
I'll show you in a few slides if I get to bit. Hadja, student of Elliott Potter, did the ray tracing. There is an interesting effect. It seems that the submillimeter dims for a certain range of R. I'll get to it.
We can talk later if the answer is long, but I think you are arguing that the duty cycle, so to speak, that you get out of these reconnection events, that somehow correlates with the flow I showed before for, episodic accretion.
Yeah.
Perhaps it's not obvious. I don't see the simple connection between these two things in the sense that in my mind, at least naively, I would not expect a lot of mass, so to speak, to participate in these events, whereas you are saying that actually this does modulate accretion to a black hole. This reconnection taking place here is pushing plasma like this. I can see some relation, but I guess if you were to put the density, naively I would think that most of the mass would not be affected by this kind of event.
I think you're correct. So I was not necessarily saying something about the mass. There is an effect to the mass in the sense that the disk is ejected. And if you, for simplifying assumptions, assume that the disk is ejected over the whole angle now, as if it were axisymmetric, just to make my argument, then the mass accretion rate would practically go to 0. There's a little bit, a few plasmoids falling in, but it's close to 0. At least it drops by orders of magnitude. So that's the effect on the mass accretion rate. But what I was talking about is that reconnection here, it expels vertical field. So it expels magnetic flux, pushes it back into the disk. And then that field in the disk, it does something, it's redistributed through, say, maybe Rayleigh-Taylor instabilities or other mechanisms. But at some point it accretes again. And so these cycles of pushing away the field and then the field accreting again with infalling matter, that is what I was hinting at. Yeah.
What's the typical time scale for these?
So the accretion events last for a few thousand RG/C. You see only 3 here because the simulation was expensive. Like you would like to do this for 10 to the 5, 10 to the 6 RG/C to know if this is just a coincidence or if this is like statistically it always looks like. I mean, I don't know. There are lower resolution simulations which indicate that this cycle keeps on happening if you simulate very long. I think it's a reasonable thing to think, but statistics are important to understand. The flux eruption periods, the large ones are typically about 100 RG/C. But very closely, you also see dips in the magnetic flux on the horizon here. So they're like small events with small current sheets, which are smaller than an RG, which don't clear out this whole azimuthal angle, but just a small part of it reconnects quickly and then it stops. So it doesn't do much, but these large ones, they happen, about every few thousand RGs.
So to that point then, do we have a sense for how dependent this is on the feeding on the initial?
Yeah, no, but it's a great question. I mean, I asked Sean Restro when he showed his simulations at the BCTS meeting, like, can you look for which configurations of feeding wind-fed accretion or for MD7, like different types of feeding, do current sheets even form? I'm not sure, like in all configurations, I'm not sure. Maybe it can give us a link between flares and the large scale accretion. Would be very interesting. Maybe the periodicity is different. Maybe there is no periodicity at all. Maybe current sheets form under an angle. Maybe they form at not so highly magnetized regions, like not the jet. All of these questions are unanswered. I'm very interested in.
What made you choose this particular initial configuration?
Say that.
What made you choose this particular initial configuration?
I mean, this is the standard setup that, let's say, the EHD runs. So the main question was, if we run the standard setup at a 10 times higher resolution, will we be able to capture reconnection at the horizon? That was the first order question. Because it's not obvious that it happens in 3D in the first place. It happens in 2D, but in 3D, it wasn't clear if that reconnection layer wouldn't be just destroyed before it would even form. Neither to me, I wasn't convinced that we would find it. Okay. Right. So I think this comes back to your question before. So if you look at the accretion during the accretion phase, these are the field lines. Blue and green they're the same types of field lines that are not to be distinguished here. They're all falling onto the black hole. This is the inner 10 Schwarzschild radii approximately. You see the plasma is cold. This is temperature in terms of pressure over density. So you can see it as the ion rest mass at temperature. So it's everywhere below 1, so it's non-relativistic. All the field lines are acute. Then you go into this flux eruption state. And now I see the field lines at the same points in space. And you see that the blue field lines are pushed away. So these are the field lines that are in the disk, and only a few of them reach the black hole. So this is the small angle of phi on which accretion still occurs. So only a few field lines of the disk can reach the black hole. Most of the field lines in the inner 10 RG are in this current sheet. And now you see that the current sheet is also hot. So it's heated by reconnection to a temperature that's proportional to the magnetization. That's what reconnection does. The magnetization here is 25. The temperature maximum is 25 here. So we know that from local box, reconnection can heat the plasma proportional to the upstream sigma. 25 is just our floored sigma, so that's by no means a realistic number, but it's good that at least some properties of reconnection are seen. And now if you zoom in on the right, then you see what you were asking. So here you see an X point. So these two field lines, they reconnected. They form two new loops. The purple loop falls in and the green loop can move outwards. And here you see this small vertical field component that has formed. So if this loop moves further outward, this vertical field will be stretched out. If you jump into a local frame and you put your coordinate axis along these field lines, then what you see is that the toroidal and the radial component reconnect and there is no guide field. So you can see this as on practically in a simplified version on the equator, the toroidal field lines at the base of the jet are reconnecting because in the upper hemisphere, they're pointing outwards and in the lower hemisphere, they're pointing inwards.
Practical technical question. How did you actually make those? So you took a sample of the magnetic field in the midplane and proportional to magnetization or something?
You mean this plot?
No, sorry. The left two plots. So I understand how you trace the field lines. You just start with like anchor points.
Yeah.
So I'm just trying to understand what the density means, density of field lines.
Yeah, it's trial and error, to be honest. I don't think there is an automated, maybe, Vladimir has done these things for like turbulent boxes as well.
How did you find the field lines that are at the reconnection point? They should wander away exponentially from the
trial and error again.
Oh my gosh.
Yeah, it took a year to analyze this. Yeah. No, but we're really like, there were more, and I'll show you some in it. Actually, probably not, but yeah, you have to look very carefully and seed field lines at a specific zoomed in point. With pair view, rotate it, go around it, yeah, in the end, I found a few of these examples, but it was not, it didn't just pop out. I mean, here you don't see them. So, yeah. Dr. Filipov likes to call it surgery on your data. Okay, how can we improve the MHD model? There are many ways. I will talk about one. But we can do general relativistic particle and cell, solve these Vlasov equations on the grid with this cycle. I will not go into it. What's interesting though is that in principle you can use this particle pusher also in MHD simulations. If you're certain that you're resolving the scales at which particles would accelerate and you have an accelerating electric field, then you can try this in MHD. We have such a pusher in our MHD code. I didn't dare using it yet because I'm not convinced of being able to resolve the proper scales. Definitely not in a global sim. It's possible in the future. What you can also do if you have such a graphic code is set up a simplified example, because doing a 3D accretion is still impossible. So what we did was we set up with Ashley Bransgrove, it's coming to PCTS next year, a current sheet at the horizon of a black hole. And there's no accretion disk here, just highly magnetized plasma, split monopole that forms the current sheet. And it does sort of the same thing as you saw in the magnetically arrested disk simulation. You see plasmoids in the ergosphere falling inwards, outside the ergosphere moving outwards, and they bring out some vertical flux. This was resistive GRMHD in 2D. If you do it with...
Can I ask that the resistivity in simulations is much larger than the realistic value?
Yes, correct.
So does it affect the reconnection rate also?
No. If you go to resistivities such that your Lundquist number is above 10 to the 4, then your reconnection rate becomes asymptotic, 0.01 of the speed of light in this simulation, if I measure it. If we go to higher, to lower resistivities, which we tried, we can do a range of like 3-4 orders of magnitude with our code, but then the code cannot resolve it anymore. You indeed see that if you plot reconnection rate versus Lundquist number, which is like 1 over resistivity, then you see something like this. This is 0.01, like here is, for example, 0.1. Here you see 10 to the 4. Here you see 10 to the 2 Lundquist number. And we sample this like pretty robustly with dots like this, where we see that this reconnection rate indeed asymptotically becomes 0.1. So this simulation is in that regime where the Lundquist number is above 10 to the 4. And yeah, we confirm that the reconnection rate is asymptotic.
What about the scale at which you have the most unstable mode?
Sorry.
The scale, the wavelength, is that sensitive to the Lundquist number? You're saying, if I have two finite points like this, you're saying that the rate at which things reconnect does not saturate, so to speak. But then I could imagine that the wavelength of the unstable mode that produces that may be sensitive to the Lundquist number. Is that the case?
We didn't look at that. I mean, you may ask Mooney sitting next to you, who may know this much better than I do, but I would propose asking after the talk.
You have 10 minutes left.
Yeah, that's it. We can talk about that after. So if you do this with grpic, you see some immediate differences. And what's interesting is that the plasmoids grow larger in grpic. So with particle and cell, if you're resolving scales, the reconnection rate is about 0.1 times the speed of light, which allows reconnection to either happen faster or to grow larger structures in a smaller times. A bit of both happens. So you see larger plasmoids in the particle and cell simulation. And if you now plot this magnetic flux that I showed for the magnetically arrested disk, then the upper lines, the blue ones, are the MHD case, where the flux decays with an exponential timescale of e to the minus t over 500. And I didn't show you this before, but we measure exactly the same e to the minus t over 500 for the magnetically arrested disk case during a flux eruption, which told us that it really has to be magnetic reconnection that's doing that, because you can link this directly to the reconnection rate. You do this with particle and cell, you see that this rate is faster. It's e to the minus t over 150. So it's about 3-4 times faster. It's not exactly 10 times difference because there's some global effects. I will not go into what exactly those are. But what you see is that with the particle and cell simulation, the flux decays faster, i.e. reconnection rate is faster. Okay, this is just how we use the grid. It's interesting. With MHD, we can do the 3D simulation. And what you now see is the same spiral and current sheet without an accretion disk. You see now that all the field lines are in the spiral, and all of them are reconnecting, and the reconnection happens indeed on the equatorial plane. So also here B phi and BR are reconnecting, and also here it was possible to find some X points and to find some of these, well, helical flux tubes, which in 2D you would call plasmoids. Whether you want to call them plasmoids in 3D, I don't care. It's your choice. So we could simulate, actually we, meaning Alisa, who did great work, a simplified model for accretion in GRPIC by just doing Bondi accretion, spherically infalling matter with a vertical field put on top, or some turbulent field. And what's now interesting is that in this 2D GRPIC simulation, you have in principle electrons, positrons, and ions. Ions with a rest mass that's not realistic. That's not the point. What you see is that during a flux eruption, which is already nice that you see that these flux eruptions happen in the first place, there is a current sheet, and this is the ion density. So here in this region, the ion density is practically zero. So around the reconnection layer, there's really only periplasma, and the ions are in the disk. So this assumption of that the jet is mainly periplasma here, and that's periplasma feeding the reconnection layer is reasonable. And also here you see this flux decay rate. You can compare MHD and PIC, and they go again with the same difference in the rate. So in the GRPIC simulation, the flux is expelled faster due to the higher reconnection rate. After the first flux eruption, the simulation still looks fairly similar. Afterwards, they diverge, but you see current sheets on both sides. You see blobs on both sides, slightly different sizes, but globally speaking, the simulation shows very similar results. There are important differences. I will not go into it. Alisa is much better at telling that. But what's interesting is if you measure the particle acceleration in one of those current sheets, you see that indeed a non-thermal tail forms, and also in this exhaust, these blobs, there are a non-thermal part. So great. We have our mechanism to power a flare. Can we understand that a little bit better by looking at theory without doing a simulation? So this is a figure made by Haik Akobian. If you ever need a figure for a presentation, go to Haik. But not too much, because then he will not do it for me anymore. So here you see all the mechanisms that we think are at play for MED7 around this reconnection. So this plasma is highly magnetized. The field is about 100 Gauss. And we think particles practically radiate immediately when they're accelerated. The cooling time scale is very, very short. You can estimate this. They get synchrotron emission. Then that emission can, in principle, pair produce. And those pairs themselves, they can go back into the reconnection layer, re-accelerate, and they can also give you some secondary synchrotron. So there are two synchrotron channels. And then there is also background radiation from the disk, which is constrained to a certain extent by observations. And all these photons can be upscattered, so either synchrotron self-content scattering or inverse content scattering on the seed photons. Well, if you zoom into this reconnection layer with the local box particle and cell simulation, you can include all those effects. And that's what Haik did. So this is a simulation with periplasma, tracking photons and incorporating synchrotron radiation, and looking at the different QED effects, like pair creation, inverse content scattering. And in that way, you can create a spectrum. And what's particularly interesting is that this is an effect due to secondary. I'll not talk about it. This is your X-ray component coming from synchrotron. And this is your TeV component from inverse Compton scattering of mainly seed photons. So this reconnection layer for properties of MED7's jet plasma can give you a spectrum that gives you the right shape for TeV flares from MED7. This is the first try into the many things to still be understood. I want to say a little bit about Sagittarius A star, but we'll skip this. The main conclusion here by Sean Ressler is that also Sagittarius A star may be in this magnetically arrested disk state, even though we don't see a jet. There may be a jet, there may not be. It may dissipate, it may just not be observable. We don't really know. But if you wind feed an accretion from global scales, then it seems to, at least in some cases, go to this magnetically arrested state and nearby the horizon. So you would expect that maybe a current sheet can form, but like George asked, is it clear that it happens? Okay, I'm going to skip all of this. I just want to show you. Let me show this for you particularly. So if such a current sheet forms, regardless whether it's MD7 or Sagittarius A star, I think this was for MD7. What you see if you ray trace it, you see your typical, let's say, EHT image, not very well resolved. This video we have better resolution. At some point, you see that the ring actually dims, which is quite interesting. So it happens about here, and this is exactly when a flux eruption happens. And the way you can see this is that during a flux eruption, your whole disk is ejected. If it's a large flux eruption, and if it really covers this full 2 pi, then your disk is ejected to beyond 10 RG. So you don't see the radiation from the disk anymore. You simply just see the reconnection layer. But that reconnection layer is very hot. In principle, it will only show non-thermal emission. And the non-thermal emission will typically be at higher energies. It will be X-rays or TV. It may do some sub-millimeter, but the flux is probably very low. So we probed this a little bit. If you go to very high values, you could be able to see a little bit of the sub-millimeter flux, but typically your light curve will look like this, and the gray bands here indicate a flux eruption. So you see that your sub-millimeter flux goes down during a flux eruption. Also, this is to be understood for schedule.
So just there's little knots in the image. A little
Right here.
no, so like if you at like 8 o'clock within the time ring. So those are I see them all. What are they?
My feeling here is just that this was a low resolution first try, and didn't yet send me a video of his high resolution ray tracing.
I mean, so I have seen them in every image that they seem to persist at what I consider to be high resolution, low resolution. Okay, so
All the images of the PTS workshop that Lisa was showing also had that.
Interesting. I don't know. I mean, Benjamin Crancot argues that you may even be able to see individual plasmoids. I don't think it's the case. Maybe it is in simulations where plasmoids can grow very large, but in reality, those plasmoids would be extremely small, I think. But yeah, I don't have proof for that. It would be interesting to understand further what it is.
I see you now understand better the connection between the reconnection events and matter not being able to accrete. But do you really see this reconnection taking place on most of the 2 pi?
Yes, we do. Yeah. Let me see if I have an image quickly.
That's okay. That's okay.
Yeah, maybe you see it here. So this will be the last slide that I show. So here you will see a reconnection event about to happen now. It's heating up. This is temperature. And what the reconnection does, it pushes this vertical field into the disk. Now it's accreting again, but here you see this vertical field still being in the disk. So it's like a huge flux
This lies in the 3D simulation.
This 3D simulation, yes. So this flux tube here, you see already from this view that it's pretty big. But if you look at it from the top, it's this huge low density, this is density plot, huge low density region here.
Maybe worth pointing out that's 2 slices.
Yeah, exactly. So it's a 3D view, but like 2 cuts. So this is the equatorial plane, and this is the, what do you call this? Colloidal plane. Exactly. Thanks. This is the jet. This is like the disk, and this is such an ejected tube, and you see this vertical field here. So you see, and like it will move further in this direction and cover this whole space. I definitely have better plots. But what is interesting is that, you don't see this here, before this flux tube forms, the current sheet itself, it also covers almost the whole azimuthal angle. What's an interesting question is that always the case? Or did we just capture one flux eruption that was huge? I think there will likely be a distribution of flux eruptions, some that are small and capture only a small part of the angle, and some that are huge and really push out the whole disk. And obviously, if the flux eruption is smaller and it doesn't push out the whole disk, and also the image will not dim in this way of thinking. Yeah, I think I'm gonna stop here. See.
So it's in the way this works naively is that when stuff is accreting, you actually manage to bring the opposite fields together. So the reconnection is mostly happening because of the radial component to be able to be such a global phenomenon. I cannot see how I don't know. That's it.
So the toroidal component that reconnects is the component of the jet, not of the disk. So
this happens over 2 pi.
And that happens over 2 pi. So in principle, it's the base of the jet, or if the black hole is spinning at least, the field at the base of the jet does this. And that field is fully reconnecting in all directions.
But when the field is doing like this, right, the toroidal component, they are pointing the same direction, at least on some reasonable, big scale. Those are not going to reconnect.
No, only on the equator. On the equator, they're pointing in opposite direction, and they're reconnecting.
Ah, okay. Because in the image that you showed before with all of the fields, it was not clear that globally speaking, at the equator they were actually opposite. But that is okay.
On the equator.
Okay, thanks.
I know it's complicated topology. It took me a while to.
I understand.
Thanks for asking.
So on the equator, basically the field line is something like that. You both have the rotation, twist, and the vertical opposition. And
Yes. If I understand your gestures well, then yes. Yeah. I have many more things to tell, but that will be for another case, another time.
We have had many questions during the talk, but if you have other questions.
Maybe just one quick one. I mean, there's a lot going on in those, events and in those images. The reconnection sites you identified are really very small little volumes and so on.
Yeah.
So will you be sure that they're really the dominant place where the acceleration is occurring, given all the other stuff that's going on? And so if you were able to do a full GR pick and follow the particle acceleration, including the accretion, not just sort of experiments of reconnection, but actually doing the full thing.
Yeah.
Are we certain that that's where?
No, not at all. Not at all. I think, first of all, this was, like someone asked, this was just a standard EHT MAD,
Right.
which sort of has to form a reconnection layer
Right.
on the equator. That's, I wouldn't say an artifact of the initial condition. It's definitely a result of the initial condition or the inclination angle. Second,
if you just calculated the entropy production rate or the heating rate everywhere in the volume, you'd be able to identify these reconnection sites as being, hotspots or.
Absolutely. I mean,
So that's a good sign. That
I don't have an.
They stand out.
But I guess what I was trying to understand is that, this, in order to prevent accretion from, taking place, it has to be a global phenomenon. So the reconnection, I agree, it's important to understand that it cannot be that small scale, right? You cannot have, reconnection on a small scale and yet have the global phenomenon.
I agree.
Yeah.
Yes.
So that's the reason.
So the way I try to sort of sell this to people without having them think that I solve everything. Typically, I'm not saying, but sometimes other people think that I'm saying, right? So, like we see this reconnection layer during the flux eruption. This is like a macroscopic one, few RG. From my MHD simulation, I practically only conclude like this thing forms. It's large, it forms. It's pretty robust. We see it in multiple simulations now in multiple different configurations. This is the only reconnection that we can resolve with current, even with the high resolution simulations, because it's a macroscopic one, and that's exactly what you're saying. But in the accretion phase, when there's no big layer here, then like there's turbulence here everywhere. There are reconnection layers in this turbulence that are forming. We see them, but they're unresolved. So when we see them, I mean, we see anti-parallel field forming in this disk, which may locally dissipate energy. The interesting thing here is that here sigma is, let's say for MED7, maybe 10 to the 8, just quoting a high number. Here sigma is maybe 1 or something. So this reconnection is energetically very different. Something we're also trying to understand, but it will clearly give different emission signatures. This may be responsible for EHT emission or for a small non-thermal component to EHT emission. The reconnection may form an imbalanced turbulence, which gives it very specific properties.
So on the right figure, you know the turbulent energy and magnetic energy ratio?
No, I didn't look into that.
Because usually in peak simulations assumed to be delta B or B is equal to 1, but it's on very small scales. So then if I extrapolate those things on large scales, the turbulent energy should be much larger than magnetic energy. Just don't know whether this is realistic or not.
So that's realistic. And I would say, I'm not sure that the GRMHD simulation can give you the answer whether that's realistic. I don't think.
So in the first phase, do we know that the current sheet is just one 2D more or less surface, or it will, break into like more or less a 3D distribution of many sheets?
It seems to
like if you increase the resolution, suppose we can increase the resolution for many times, do we expect it to still keep these more or less?
So if we increase the resolution from, let's say, the EHT resolution by factors 2, then you see practically in let's call it an EHT resolution simulation, you also see this current sheet form. It's just broader. Those flux eruptions are in EHT simulations, they're in everyone's MAD simulations. It's just that this layer is broader and it doesn't fragment into plasmoids.
Do you mean, is there like a fractal dimension?
Or more or less, whether you can, when simulating these, whether you can assume it's just a simple geometry, or actually what happens is it is a turbulence. It's just a global.
100% a very turbulent thing. 100%.
Okay, so that means if you zoom into a very small scale, then more or less it's like a turbulent. A turbulence box will better simulate that instead of having
whether it's a turbulent box or a 3D simulation of a forming reconnection layer by pushing flux together.
Yeah,
that becomes turbulent. I don't know. I think it's more realistic is to think, because in principle your field here and your field here is compressing. Yeah. So if you were to draw a box here, it will be as if like this field and this field is being pushed together by the.
But imagine at large scales you have these regular field lines, but if you zoom into very small scales, mostly quite.
Here it will be turbulent.
So when you say turbulence, do you mean turbulent cascade or tearing stability?
I mean, definitely tearing instability.
So it's not MHD turbulent cascade, right? Because these are two different regions of reconnection that are studied in the literature.
Yeah, I think how I would call this is a 3-dimensional turbulent reconnection layer. There are simulations of that. Like you push together 2 flux tubes in 3D, you get a turbulent 3-dimensional reconnection.
We see the transition from tearing instability to MHD turbulent cascade. If you measure the spectra and isotropy.
We don't have the resolution to do that here. No.
Okay.
Do we have time?
You
can also.
Sure.
Okay. One of the things that we discussed at the PCTS workshop briefly is the fact that pretty much nobody can make a simulation where the 1.3 millimeter image would have the jet be brighter than the core.
Yeah.
And I was just wondering whether you had done anything in terms of like probing the kind of allowed parameter space of the radiative transfer and what the effect of these, not just the really high resolution, but also the resistivity might have on that problem.
Yeah, it's an interesting question. No, I didn't do that in terms of ray tracing, but Jordi Davelaar is working on that or thinking about that at least. I haven't seen any results, but I gave him the data and like do your magic. Resistivity will not have an effect. Resistivity is more or less a knob that you can turn in an MHD simulation to control your dissipation, to understand your dissipation. Like for the questions you're asking, there will be no difference between ideal MHD and resistive MHD. For the heating, let's say. And ideal MHD will be on the grid scale, but it seems to be doing very similar things. Why exactly that is, not 100% sure. But what's interesting as physical mechanism is sort of two things. One is this reconnection layer here is very hot, and it expels hot material, and the temperature, and I mean ion temperature, is proportional to the sigma in the jet. So if the sigma is very high, which we are not probing because of density floors, your temperature of ejected material is very hot. It will cool down, of course, which is also something we're not capturing. But if you sort of extrapolate in your head, then it will eject like hot material into the jet boundary. And if you could trace that with high resolution along the jet, you would see it like travel along the jet. How long it lives and how long it travels, I don't know. Can it explain sort of long-term limb brightening? I don't think so, because like it happens only during those flux eruptions, right? So only for a few hundred RG over C, and then it would have to travel for thousands of RG. So I don't think that happens. Maybe it does. But what is interesting is that stuff bumping into this jet boundary, what it will do is it will induce waves here. Whether these are waves, that they do Kelvin-Helmholtz or not doesn't really matter. But what we see is like, if such a huge chunk like bumps into here, like it induces a wave, and this wave can travel and can heat. I think actually George saw this in his simulations 3 years ago or something, 4 years ago. We see it too. And what's interesting is that those waves seem to happen only after a few flux eruptions have happened. In the stage where you're in like a semi-mad or in the sane stage where first flux eruption hasn't happened, this jet boundary remains very laminar, which is of course, again, like it's initial condition build-up phase. So it doesn't say anything. But what's interesting, you will have many of those flux eruptions. So this will be a continuous thing and dumping stuff in the jet boundary. Could it limb brighten? Probably. Will it give the right signal? I don't know.
So we are now 15 minutes over, so I think we should definitely stop. You're going to be here for several hours?
Yeah, I'll be here.
Okay, so let's thank Bart.